Here we're looking at section 7.3, double angle formulas. So the question is, can I come up with formulas for, say, sine of 2x and cosine of 2x in relation to sine of x and cosine of x? So actually, this is going to be pretty straightforward. So say I look at the formula for sine of 2x. Well, can't I write 2x as x plus x? And then can't I use my formula, the one for sine of s plus t? Remember that one from the last section? So how does that work? Sine of the first, cosine of the second, plus sine of the second, cosine of the first. It just happens that here, well, the first and the second are the same. So wouldn't it be true then that sine of 2x, I have like terms, 2 sine of x, cosine of x. So there's my double angle formula for sine. Let me do the same thing for cosine. So now I need my formula for cosine of s plus t. So for that one, remember I do both cosines, cosine of the first, cosine of the second. Plus here is opposite minus here. Sine of the first, sine of the second. It's just that in this case, again, first and the second are both x. So wouldn't it be true then that cosine of 2x would be cosine squared x minus sine squared x? So there's my first variation of the double angle formula for cosine. Now, this formula, I can actually come up with a couple other variations. The reason why is because remember that the fundamental identity says cosine squared plus sine squared is equal to 1. So wouldn't it be true then that cosine squared is 1 minus sine squared? So what if I do a substitution? So what I'm going to do here is I'm going to come up with a couple of other variations of this formula. And what I'm going to do is I'm going to actually take this guy and I'm going to substitute it in for cosine squared here. So what is that going to look like? Isn't that going to be then cosine of 2x is 1 minus sine squared x minus another sine squared x? 1 minus 2 sine squareds of x? So there's another variation of that formula. Okay, now what if here, instead of solving for cosine squared, what if I solve for sine squared? Okay, and then that's going to substitute in here, or sine squared. So there's my third variation of that formula. So let me write out a summary then. So I guess here are my double angle formulas. So my sine of 2x, I just had the one formula. And then my cosine of 2x, I had 3 variations. Okay, so these formulas are very useful. See what some of the applications are. So here's an example. Find sine of 22.5 degrees. So the thing is, 22.5 is not actually a special angle. However, I know 22.5 degrees is half of 45 degrees, which is a known angle. So when I'm looking at these, I'm really looking here and I'm saying, well, which of these formulas am I going to be able to use here? So what am I actually looking for? So let me think about which formula I might apply. I mean, if you kind of just look at it, you might think, well, the first thing I would try is maybe I want to use the sine of 2x formula. But actually, if you set that formula up, look what you get. Okay, sine of twice 22.5, sine of 45 degrees is 2 sine of 22.5 degrees, cosine of 22.5 degrees. So is this formula going to give us what we want? Okay, well, I know this value. This is what I'm looking for. But this one, I'm stuck. I don't know the value of this guy. So I can't actually use this formula. The thing is here, I'm not actually looking for sine of 2x. I'm looking for sine of x. So if you look up at the formulas, actually for this type of problem, I'm always going to be choosing between these two formulas. Okay, because look at what happens. Which one am I going to use? Well, it's going to be this one, because actually what I'm looking for is this quantity. So you see with these two formulas, the left side is always cosine. What determines which formula that I'm going to use is going to be on the right side here if I'm looking for sine or cosine. Okay, so in this case, I'm going to choose this formula. So I'm going to have cosine of 45 degrees is 1 minus 2 sine squared 22.5 degrees. So cosine of 45 degrees is root 2 over 2. So you see, now all I have to do is do the algebra to get this quantity by itself. So let me see, let me subtract the 1. Let's do an LCD. So what would that be? Root 2 minus 2 over 2? Okay, divide by negative 2, or isn't that the same as multiply by negative 1/2? So then what? I guess I would reverse the order of these. 2 minus root 2 over 4. And then take the square root. Now in the numerator, I'm stuck because I have that difference underneath the radical. But in the bottom, let's see, square root of 4 is 2. Then I just have to decide, well, which quadrant is 22.5 degrees? It's in quadrant 1, right? So in quadrant 1, the cosine and the sine should both be positive. So that tells me which sign to choose here. So because I'm in quadrant 1, I know the sine of 22.5 degrees would be positive root of 2 minus root 2 over 2. So really what I've done here is I've used a double angle formula, but actually I've used it to find a half angle. Okay, because 22.5 is half of a known angle. Here's another half angle problem. As in, you see how, okay, well, let me look at 5 pi 12ths for a second. Maybe you don't see it yet. But if I take 5 pi 12ths and I multiply it by 2, it's 5 pi 6. This is a known angle, right? So indeed, 5 pi 12ths is a half angle. So let me see which formula I would use. So for any of these half angle problems, remember I'm always choosing between these two. Okay, now in this case, because I'm looking for cosine, I'm going to use this guy because this is the quantity I'll be solving for. So then I'm going to set this up. I'm going to have cosine twice my 5 pi 12ths was my 5 pi 6. Like so. Okay, and then I evaluate, let's see, 5 pi 6 here, right? So negative root 3 over 2. And then I just do the algebra, solving for this cosine. So add the 1. LCD, 2 minus root 3 over 2. Okay, needs to divide by 2, or essentially multiply by a half, right? Take the square root, and then I have to pick the branch. So numerator stays under the root. Square root of 4 is 2. Which quadrant is 5 pi 12ths in? Well, I guess 6 pi 12ths would be pi over 2. So 5 pi 12ths is here. So again, this is in quadrant 1. If it were in quadrant 2, I would choose the negative branch. But because it's in quadrant 1, I'm going to choose the positive branch. What else can I do? Say I know cosine. Cosine of x is negative a third. X is in quadrant 2. Find cosine of 2x, sine 2x, tan of 2x. Okay, well, I've got 3 formulas for this guy, right? To decide which one would be the simplest choice with the given information. Well, look, I'm given cosine of x. So the only one of these formulas that has only cosine of x in it is this one. So that would be the simplest choice. So I'll go with that formula. So cosine of 2x is 2 times cosine of x squared minus 1. So 2 times a ninth, so 2 ninths minus 9 ninths, negative 7 ninths. There's that. Now I have a couple options. So I found cosine of 2x. So that one's done. Now I need sine of 2x. So I guess one thought would be, well, what if I construct a triangle according to this information? So a triangle for the angle 2x. So I'm just kind of thinking, well, I wonder if I could figure out what quadrant that I should place this triangle in. So let me see, if cosine is negative, I really have two options, right? Either I'm here, this has to be negative 7, and this has to be 9 either way, right? In order for cosine to be negative 7 ninths. But I don't know yet if I'm here in quadrant 2 or here in quadrant 3. In other words, I don't know if the y would be positive or negative. Now notice these are triangles for the angle 2x, not the angle x. You see how in the instructions here, where are the instructions? Oh, right here. What it says here is it says the angle x is in quadrant 2. But what about 2x? I wonder if I can figure that out. So if x is in quadrant 2, let's see, that means x has to be in between here and here, right? So if x is in quadrant 2, then wouldn't it have to be true that it's in between 90 and 180 degrees? What if I multiply by 2? So that means the angle 2x has to be in between 180 degrees here and 360 degrees. So wouldn't it have to be true then that the angle 2x in this case has to be in quadrant 3? Okay, because that's the only way that it's going to have a negative cosine and also fall in this set. So that means the triangle that I'm dealing with is, this one here, right? In other words, the y is negative. So if I set up my Pythagorean theorem, what does that come out to? 32? It's plus or minus 4 root 2. So again, I know y has to be negative. Okay, now I can go ahead and fill in the values. For sine of 2x, that'd be negative 4 root 2 over 9. And tangent. And so there we have it. Here's a couple simplifying problems, and these are actually really easy. So actually these guys are really just looking at, do you kind of recognize the formula? So when I see number 1 here, I think, the first thing I see is I have 1 minus 2 sine squared of something. Isn't that one of the formulas for cosine of twice something? So actually, to simplify this, I mean, couldn't I just make this cosine of twice the 6 theta? Cosine of 12 theta? It's pretty easy. Versus this one, I see 2 sine of u cosine of u. I know that's the formula for sine of 2u, right? So this one just be sine of 6x. Here's something that's actually really useful for calculus. These problems are right in terms of the first power of cosine. In other words, these are power reduction problems. My goal is to reduce the power so I only have a first power instead of, say, a fourth power. Well, it turns out I can get formulas just by thinking about or starting with my double angle formula. Say start with this one. I can use u or x. It doesn't matter. Should I do x? Either way. Okay, here's what I'm going to do. I'm going to solve for cosine squared. So I guess I'd have to add the 1, divide by 2. There's a power reduction formula for cosine. In other words, okay, I know I can relate cosine squared to the first power of cosine according to this formula. What if I do the same thing, starting with this formula? And now I'm going to solve for sine squared. So add 1, or I guess it would be subtract 1 this time. Okay, so sine squared x So if you look at this formula, this is the power reduction formula for sine. You notice that these two formulas, power reduction formulas, look very similar. One is a plus and one is a minus. Okay, so now I don't think I'm going to need both of the formulas for this problem, because in this problem, I actually only have cosine. So I'm going to start by making cosine to the 4th, cosine squared times cosine squared. Then I'm going to need this formula. Need that formula twice. Okay, so let me do some algebra. I'm going to have a 4 on the bottom. This is a FOIL, right? It's 1. Let's see, plus a cosine of 2x plus another cosine of 2x plus 2 cosines of 2x, and then plus a cosine squared of 2x. Okay, so I'm getting there. Remember, my goal is to write in terms of the first power of cosine. So I've gotten from fourth power to second power, but I still have to continue because I'm not down yet to first power. Okay, so here's what I'm going to do. I'm going to go ahead and break this up. So you see how this 4 is dividing all 3 terms in the numerator there? So what if I go ahead and break this up? Wouldn't this be 1/4? Then let's see, 2 over 4 is a half. And then a fourth, like so. Because actually, if you'll notice, the first 2 terms here are done. I've already reduced the powers there. Only thing I have to deal with then is this, where I have the cosine squared of 2x. So for that, I'm going to be using this formula again. You just have to be careful because you see how the way that formula works. When you fill this in, it always looks like so, but whatever is in the bubble here has to be twice the argument down here. In other words, because this one was a 2x, this one, right? Inside here, I actually have a 4x, okay? So it's a doubling formula. So whatever I have in the argument here, whenever I use this power reduction formula, the argument on that guy is double. Okay. All right, so what else? So then let me just see if I can simplify this anymore. See, this guy divides into both of these again. So I have a 1/4, and then a half plus a half cosine 4x. Like so. And then I guess I have these like terms. 2/8 plus 1/8, so 3/8. First power there and first power here. So I'm done. So actually these guys are really useful for calculus. So you're going to see these power reduction formulas come up again and again. So these guys are actually worth practicing. Let me do one more. Same thing. So this guy's also power reduction. Okay, so I'm looking back up at my formulas. Those are right over here. This one and that one. Okay, so sine squared and cosine squared. 1 minus cosine, double that. 1 plus cosine, double that. multiply straight across. Okay, so the good news there is I actually have a difference of squares because look, I get a 1, then I get plus a cosine of 10x minus a cosine of 10x actually cancels. And then minus a cosine squared of 10x. Difference of squares, right? This guy actually turns out nice because look at this. Here's something nifty. Isn't it true that 1 minus cosine squared of something is sine squared of something? Where does that come from? It comes from this identity, right? So if I solve for sine squared is 1 minus cosine squared, right? So wouldn't it be true then that 1 minus cosine squared would just be sine squared? So if you do it that way, makes this problem actually pretty simple because then I'm just going to apply my formula one more time for sine squared. Looks like this. Remember, I have to double the argument here, be 20 then. Okay, a little easier. We've done these before. Here I need to write as an algebraic expression. So actually what I have here, this would be considered a trigonometric. It's like so. That's a trigonometric expression. So in other words, if my goal is to write an algebraic expression, my goal is really to get rid of the trig functions. So let's write that. Get rid of trig functions. So we've done this before, but let me just remind you, like, what if I had one like this? Okay, remember how we did these? So we said, okay, theta is the inverse cotangent 4/7. Cotangent theta is 4/7. Then we made a triangle. So cotangent was 4/7. Found the other side. Or something like that, right? And then we filled in the cosine, so it'd be like 4 over root 65, something like that. Okay, so we're going to do this problem exactly the same way. Okay, so we're going to say, all right, well, let's let theta be the inverse cotan of x. So cotan of theta is x. Then I'm going to make a right triangle. I need to fill this triangle in. Now, x is x over 1. So cotangent, x would be here and 1 would be here, right? Then I use the Pythagorean theorem. Like so. Notice that does not equal x plus 1. In other words, I cannot take the square root across a sum like that. I'm actually stuck with that radical. Look like that. Okay. Then I come back up here and I fill in the cosine. Be x over root of x squared plus 1. And in this case, again, these are important ones for calculus. Usually we'd be doing something more with this. In other words, like I would maybe be finding an integral, say, after I've done this. So I would not even bother rationalizing the denominator. Actually, the expression would become more complicated. So I would say here, don't bother rationalizing. Here's another one. So theta is the inverse sine. Sine of theta is x. X is x over 1. Make a right triangle. So sine, x would be here, 1 would be here. So how about we'll call this one L. L squared plus x squared is 1 squared. Again, I cannot separate that like so. That would not be correct. Okay, so instead, I'm going to leave that. Like so. And then what do I need here? I need tangent. So that would be x over root 1 minus x squared. Again, I wouldn't bother rationalizing. Okay, a couple more, same idea. This one's a little more interesting because first thing I see is I actually have a cosine of a sum. So remember the formula for cosine of a sum. It's like so, right? Okay, so how does this work? Then it's cosine of the first, cosine of the second, minus sine of the first, sine of the second. Let me make sure I copied that all down right. Looks like it. Okay, now each of these I can evaluate like above. But actually what you'll notice is I actually only have 2 inverse trig functions here, right? I've got inverse sine, and then I've got inverse secant. So I actually only need 2 triangles. Look. So I guess should I set this up? I'll need 1, 2, 3, 4 bubbles. Okay, but then let me look at the triangles. So I've got, let's see, 1 for inverse sine of x, and 1 for inverse secant of y. Okay, so I think we did this one earlier, didn't we? Pythagorean theorem. Let's finish this one. Okay, secant's the reciprocal of cosine. So if it were cosine, it'd be y here and 1 here, right? So it's vice versa. Y here 1 here. I need to find this other side, call that h. So this guy would be square root of y squared minus 1. Okay, so then I'm looking back up at the top here, and I'm going to start filling in bubbles. So now I need, for my inverse sine triangle, I need the cosine. So let's see, that would be this guy or that guy, right? Okay, now for my inverse secant triangle, I need the cosine. That'd be 1 over y. Oh, this one's easy. That one I can actually just cancel, right? I have x over 1. Last one. For my secant triangle, this one, I need sine. So that'd be root y squared minus 1 over y. So I guess we already have an LCD, don't we? And there we have it. Okay. And so one more, I might do a couple more here for you. So same idea. First thing I notice here is I have a 2 inside. So to me, this looks like a cosine of 2 times something. Okay, so I know I have 3 formulas for the cosine of 2 times something. There's that one, and there's that one. So I can actually use any of those 3 formulas and I would get the correct result. So I mean, if I set this up, let's see. So I guess my options would be cosine squared of inverse sine minus sine squared of inverse sine. Or I could do 2 cosine squared inverse sine minus 1. Or I could do 1 minus 2 sine squared inverse sine. Now again, any of these 3 should get me the correct answer. Kind of looking at these 3 and I'm thinking, well, what would be the simplest choice? And I think this one would be the simplest choice. Because if I write my cosine of 2 inverse sine in this way, well, isn't that the same? I can move the squared, right? Like so. Can't I actually cancel these? And doesn't that just leave me with that? So actually, wouldn't that be the answer? Now, I mean, I can use a different formula. Like what if I use this one? Okay, it's just going to be more work, but let's try it. So what if I said instead, I'm going to use this formula. so again, I could move the squared outside. Thing is, I have to figure out what the value of this is, right? So for that, I'll have to make a triangle, right? We've done this, right? I mean, my triangle is again for inverse sine. It's like that, right? And then what is the cosine? Would be root 1 minus x squared over 1. Okay, so look at that. See how I got the same answer here and here? Of course, the top one was less work. I don't know, can I come up with another one for you? Maybe one with a sine. How about sine of 2 inverse tan? Okay, so when I see that, I see a sine of 2u problem. I know I need this formula. Okay, there's only one formula for sine of 2u. Okay, so this is going to be sine of inverse tan cosine of inverse tan. Okay, so I'll have to find the two pieces of information, this guy and this guy. Of course, both of those I would use the same triangle. Okay, so let's see, what is sine? That'd be x over root 1 plus x squared. And cosine, and so 2x over 1 plus x squared. That comes out